Okay, I believe it is time to get started with the last part of the conference Elliptics and beyond. We will have two talks, and the first talk is by Lara Anderson, who will speak or present an overview of Calabi elliptic fibrations. Could you, yes, please share your screen? Thank you.
So let me begin by thanking the organizers. This has been a fun week for me to participate in virtually. I don't work in amplitudes at all. My specialty is string compactification. So this has been a fun overview of the sort of the state of the field and a lot of interesting open questions for me. So thank you for giving me the opportunity to see a glimpse of this. As was mentioned, I was asked when I was asked to speak here to provide a pretty broad overview talk about Calabi geometry. And the target audience of this talk is non-experts in mathematics or the geometry of Calabi manifolds. So this will be at quite a broad level, I hope. And I apologize to the experts in the room. Some people know this very well, so this may be a bit boring. For most of the talk, I'll be talking sort of about general review material, and then I'll mention a little bit towards the end about some work that I have done with collaborators. James Gray, also here at Virginia Tech, and our then postdocs, Jin Gao and Sungju Lee, on characterizing elliptic fibrations in Calabi manifolds, and also some current work in progress with James and with Waddy Taylor at MIT. So that's the plan. Let's see how this works. Let's see, there we go. So the motivation for considering Calabi geometry that I want to give you a very broad brushstrokes on to begin with is within string theory. Of course, string theory comes with a lot more baggage than just quantum field theory. It's a powerful extension of quantum field theory, but the sort of higher dimensional nature of the effective field theories that we are naturally led to in, for example, 10 and 11 dimensions in string theory means that we are forced, in order to do physics in, quote, the real world, to the subject of string compactifications. So we have to consider solutions of higher dimensional string theories in which part of those directions of space take the form of compact manifold. The process of string theory involves not just writing down a field theory, but a path from higher dimensional geometry through to 4D physics. So the catch here is that we need a robust toolkit in order to be able to extract low energy physics from a string compactification. So in particular, in field theory, we can write down a field theory of any type we like. For example, the standard model, and we're free to choose the mass of the electron to be whatever we'd like it to be in that field theory. Within string theory, many details of this field theory, the form of couplings, the form of potentials, the form of masses, all of these are constrained by the higher dimensional solution, the fact that you have this compact manifold as part of the solution of the theory. And these aren't free knobs you can turn in terms of couplings and masses. They are actually dictated to you by the form of that compact background. So in string theory, we're frequently replacing the question of which effective field theories are we allowed to write down with which geometries are arising in these solution sets. So something that a lot of people in string theory are very interested in at the moment is a Venn diagram of the form of the one that I have here on my slide, one in which you are interested in where within the space of, for example, 4-dimensional field theories, where do string compactifications live? Do they sweep out all of this space, or are they only some of them that can be? So can only some 4D field theories, gauge theories, be extended to also include gravity, quantum gravity in a string context? And also, of course, we're interested in very particular field theories like the standard model and whether we can achieve those in a string context as well. So there's been a ton of work in string theory in this so-called swampland program at the moment, which is trying to answer questions of this type. What types of field theories are allowed? Which ones can be consistently completed in field theory, in string theory, which field theories can be completed? And can we extract patterns, constraints, predictions from these types of backgrounds in a useful way? So this is a very broad brushstrokes motivation for why background geometry in string solutions play such an essential role. Now, in today's talk, I'm going to focus on one particular type of background. This is by no means the only type of geometric solution that appears in string compactifications, but it is one that appears very broadly. And these are Calabi manifolds as solutions for the compact directions of string theory. So these frequently arise from supersymmetry conditions in 10D string theories. The condition that the internal directions of your space, the ones that you are going to choose to be compact, must be Ricci flat. So the definition that we're going to be interested in is that a Calabi-Yau manifold is a compact, complex manifold which admits a Ricci flat metric. I'm writing this here as GAB bar in terms of the complex coordinates on this internal space. So for example, if I began in 10 dimensions and I'm interested in getting a 4-dimensional theory, then I would have to have 6 compact dimensions, and that's a complex threefold. Now, Yau's proof of Calabi's conjecture showed that such a metric exists if you have a manifold that is so-called Kähler and satisfies a topological condition that its first Chern class vanishes. This is simply the trace of the curvature. This is also one-to-one with being SU3 holonomy as a manifold. Now, Yau won a Fields Medal for completing this proof and proving that for a class of manifolds of this type, a Ricci flat metric must exist. He did not explicitly write down said Ricci flat metric, and this leads to all sorts of problems within string theory in that we would really love to have that metric in order to be able to compute things that we actually want in the field theory, but this is non-constructive. So recent numeric work has worked on trying to generate explicit Calabi-Yau metrics, but in principle, they're still broadly unknown. This, as I just outlined it, was Calabi-Yaus as they arise in string theory. But of course, as we have seen in this workshop, there are many more arenas where this type of geometry is appearing naturally in field theory contexts. So in the context of Feynman graphs and scattering amplitudes, we've heard many examples this week where Calabi-Yau backgrounds have appeared. There's other known examples in the literature in which the vacuum space of field theories, for example, work by Yang-Hui He and James Gray and collaborators showed that the vacuum space of supersymmetric QCD must in fact be a Calabi-Yau manifold. So there are many examples where this type of geometry appears, and there are probably pretty broad energy minimization reasons for that to do with this Ricci flat solution. So this happens in a lot of places. So what can we say about these manifolds? So the first thing we want to try and enumerate is what types of Calabi-Yaus exist. And again, this has been alluded to in many aspects of this week, so I imagine most people have at least heard these results, but let me try and say a little bit about it. You can step up the dimension of the complex n-fold. So for a Calabi-Yau one-fold, this is unique, and this is a T2. This will also be referred to throughout my talk as a genus 1 or an elliptic curve. Just to be precise about it, an elliptic curve is simply a complex description of a T2. So T2 is a real manifold, elliptic curve is a complex manifold, and it's a genus 1 curve that admits a marked point. So it is a genus 1 curve with a slightly enhanced bit of structure. For 2 complex dimensions, again, if you exclude the product solution T2 times T2, you have a unique solution, the K3 surface, which has appeared in many talks, Matthias's and in Chuck's talks yesterday, for example. K3 surfaces are Calabi-Yau 2-folds, real 4-folds, etc. There's only one of those. So far, 1, 2 unique solutions, it's looking good, but at complex 3, things break down. There are over 1 billion topological types known so far, and still counting. We do not yet have a proof that there is a finite number of Calabi-Yau 3-folds. And although systematic attempts have been made for building Calabi-Yau 4-fold data sets, once you get to say 5 and higher, you can actually show that even the standard ways that we have of building Calabi-Yaus, you're going to rapidly exceed computational power, existing computational power in trying to classify these. So for n bigger than 3, you are going to have very large data sets of manifolds indeed. So the simplicity, unfortunately, goes out the window. Okay. So let's say a little bit about 3-folds to begin with. These are certainly, from the point of view of the topics this week, this is not the only geometries you'd be interested in. You might be interested in elliptic curves or 2-folds or higher dimensional Calabi-Yaus as well. But this is sort of the first example where we have structure that begins to be characterizable and diverse. So let's try and begin there. So as has been alluded to in other talks, a Calabi-Yau 3-fold has 2 important structures that characterize its topological type. These are the complex structure deformations of a metric. This is varying what you mean by complex coordinates on the manifold, and these lead to explicit deformations of the Ricci flat metric. It also admits a Kähler structure, and a Hermitian metric on a complex manifold is called Kähler if it can be written in complex coordinates in this form, i.e. only the 1,1 part is non-vanishing. More specifically, it can be written as dd bar of some complex function. These degrees of freedom in a string compactification would appear as 4D massless moduli of the theory. Wiggles of the metric would appear as 4D massless scalars. And the number of those would be counted by the Hodge numbers of the manifold. Again, this has been mentioned in a variety of talks. For our purposes today, this is only really important in that it allows us to characterize one Calabi-Yau by talking about these topological invariants. The H11 and H21 moduli characterizing the size and shape moduli of the geometry. Okay, so there is a few broad brushstrokes of Calabi-Yau threefolds. Now we want to get to the point that I think most people here would be most interested in, which is you find a Calabi-Yau arising in your calculation in some explicit way. You want to be able to describe it and understand how to calculate quantities of interest to you. So Yau's theorem is powerful, but how does one explicitly construct Calabi-Yaus, and how does one describe their essential properties, calculate stuff? So to begin with, we know that we want compact complex manifolds. So one naturally thinks complex manifolds that start with Cn, but of course that's not compact. So it is natural to consider the most simple compactification of Cn into complex projective space, which is to identify a set of n coordinates. Here I wrote z0 to zn up to some overall scale. So any 2 points in this n-dimensional space are identified as the same point if up to a scale they are the same. So an example, of course, P1, which has appeared in many talks, including Albrecht's just now. This is the real manifold of S2. So you can see the compact nature of that in that description. Complex projective space is sometimes written CPN. I'm going to drop the C and just write it as PN for the purposes of this talk. Complex is implied. This thing is Kähler, but not, of course, Ricci flat. It has positive curvature. So what can one do with that? You can, of course, define the zero locus of a polynomial. You can consider an algebraic subvariety, P of zi equals 0. And the notation for this, which again you've seen in a variety of talks, is to write the Pn that you're treating as an ambient space, and in brackets, an integer m, where m is the degree of the hypersurface that you're going to be defining. Now, where does this, how does this lead to a Calabi-Yau? How does this give you what you want? Well, you can just do a very basic problem in GR, which is you can say that this positive curvature ambient space has a natural Kähler metric, which looks like dd bar of a log of the squares, the norms of the complex coordinates. This is called the Fabini-Studi metric. And you can just ask, as a metric subvariety, if I just restrict to this hypersurface, what happens to this metric? So you can restrict to the p equals 0 locus. And it is a pretty straightforward GR calculation to show that the Ricci tensor, Ricci scalar restricted, goes as, Ricci tensor restricted, goes as the following. You get things that look like an integer prefactor, which depends on which projective space you started with and which degree equation you put in it, times the Fabini-Studi metric itself, plus things that are total derivative terms. Now, why is this interesting? Well, if you look at that prefactor, what you can show is that if you take the trace of this, of course, this thing, if this prefactor vanishes, then all these higher derivative terms under a trace vanish, and you will end up with the trace of the Ricci tensor being 0, i.e. C1 being 0, if you have a numeric correspondence for an m-dimensional hypersurface in a n-dimensional projective space, then you will end up with a Kähler manifold with C1 equals 0, and so by Yau's theorem, this will be a Calabi-Yau manifold. Again, just dimension counting, if we have a n-dimensional projective space, we will have a Calabi-Yau n-1 fold because we cut it with one equation. So the classic example, which you've seen in a variety of talks, is of course the quintic polynomial in P4. 0 locus of a degree 5 equation homogeneous, say of this type, gives you a Calabi-Yau threefold. Now, this idea of how to build Calabi-Yaus is useful for a variety of reasons. What we're really interested in is Ricci flat solutions to, say, string backgrounds or whatever field theories we're interested in. Those need not be algebraic. We might be solving problems in differential geometry, but by writing algebraic equations of this type and using Yau's theorem, we've substituted problems in differential geometry for problems in algebraic geometry, which in general are much easier. Not all, but in this case, many of these problems are. So what we can now ask is, how many Calabi-Yaus could I build using a technique like I just described? So consider a projective space, write an equation in it. It's easy to show that this condition to have the first term class being 0 can be naturally extended to multiple hypersurfaces intersecting. And you, again, have seen in Matthias's talk, for example, examples of this type. So you can show that the Calabi condition for multiple hypersurfaces is that the sum of the degrees of those hypersurfaces has to add up to the dimension of the projective space. Dimension of the projective space plus 1. So in this case, I'm deriving here a P5, the two elements of this bracket separated by a comma. These are saying that I write down two equations that have to be satisfied, both of degree 3. The sum of those degrees is 6, which is n plus 1 here. So this condition is satisfied. And again, this is going to be a C1 equals 0 Calabi manifold. You can step up how many equations you want to write down in bigger and bigger ambient spaces. And you can ask how many manifolds could you build? So for example, we could build a 3-3 hypersurface in P5, 4-2 hypersurface in P5. This is satisfying the numeric condition we need. 2-2-3 in P6, so on. You might ask, can I just keep going forever? Can I make bigger and bigger projective spaces, more and more equations, cutting out and continue building manifolds? You actually, for single projective spaces, you stop at the 5 that I have listed here. So the quintic and these 4 additions. The reason for that is that pretty soon, as you do the combinatorics problem of trying to write down in some Pn a set of equations that are going to give you, say, a Calabi threefold, what you find is that you have to include linear constraints in order to have the sum of degrees work out right. And in fact, a linear constraint in a Pn is just a Pn minus 1. That's easy to see in that you can just solve the linear for one of the coordinates and end up with a bunch of other coordinates with exactly the same scales, scaling properties that you had before. So there are only these 5, they're called cyclic Calabi manifolds that can be defined in a single projective space, Calabi threefolds, I should say. Of course, 2-folds and 1-folds you can do very similarly. There's a few descriptions of those, but because we know there's only the elliptic curve and the K3 surface, these are just different descriptions of the same manifold. Okay, what generalizations might one consider still further if one wants to build more manifolds? You can change the notion of scaling that you're introducing to your complex coordinates in order to make them compact. So I chose to compactify my coordinates by identifying points such that the entire vector was identified up to a scale. But you could actually scale each coordinate separately, and that's what's described here. This is a so-called weighted projective space instead of projective space. So here, each coordinate is scaling with a different power of this parameter lambda, and we write that as a p where the subscript here denotes the weight of the coordinates. So this is 1, 2, 3 because it's telling me the power of lambda that each coordinate lives in. Again, there is a simple condition on such a space for the degree adding up to the sum of the weights of these coordinates. So in this case, a T2 Calabi 1-fold could be written as a P1, 2, 3, which is a complex surface, and a degree 6 hypersurface in that. You can also generalize the description so that you have product ambient spaces. Again, you saw this, for example, in Albrecht's talk this morning. You can have, instead of having a single projective space, you can define your ambient space to be, say, a product of P1 and P2, and then write a single equation, that's what this column represents, as, for example, a degree 2, 4 hypersurface, where 2 is telling you the multi-degree in these coordinates, 4 in these coordinates. This has to be homogeneous 2, 4 polynomial in such a space. Here, this product naturally you can extend as high as you like, and for each row in this case, you have to still satisfy this Calabi condition that the degree is 1 more than the dimension of the projective space. Sorry, that should be a P3 there in order to satisfy this, P1, P3. Okay, so if you ask how many manifolds now can I build of that type, if I extend to products of projective spaces, this was actually first classified in the 1980s by Philip Candelas and collaborators at CERN. And they found that there were 7,890 Calabi threefolds that could be built in generalizations of this idea. This was a remarkable feat of 1980s computing. This was done on magnetic tape at CERN. And if you actually try and run a classification of this type, so say I want to build, I'm going to extend products of projective spaces according to this rule that the equations have to add up so their degree is 1 more than the dimension of the projective space. If you set that algorithm up in a stupid way, even on a modern computer, it would never finish. So the fact that they tuned this in such an intelligent manner to actually finish this in the 1980s was pretty impressive. And this constituted the first large data set of Calabi threefolds that had been built. So these 7,890 manifolds. You can also still further generalize this, and Albrecht described a bit of this in his talk, to more general toric varieties, changing the scaling relation, not necessarily having products, but multiple directions with different scales. These lead to also a simple way to build Calabi-Yaos as hypersurfaces or as complete intersections. And using that toric generalization of these ambient spaces, so far more than 1 billion Calabi-Yao threefolds have been built. This is the so-called Kreutzer-Skarka database, also mentioned in Albrecht's talk. Okay, so hopefully this gives you a little bit of a feel for, we went from an abstract condition for Ricci flat metrics to now we have explicit algebraic constructions in projective spaces or generalizations thereof. What else do we want to probe? So let me try and say for the Calabi-Yao threefolds a little bit about what this data set of 1 billion manifolds lets you extract. So I apologize, on this slide, my axes got cut off. This picture is a famous plot of the Hodge numbers of the Kreutzer-Skarka dataset. And the axes here, the horizontal axis is the difference in the two Hodge numbers that characterize a threefold. This is H11 minus H21, and the vertical axis is the sum, H11 plus H21. Now each dot here represents a topologically distinct manifold, a different value for the Hodge number pair H11, H21. So you have a whole bunch of dots and 500 million manifolds as written here. Now we have to say, what do we want to extract from this? So let's try and make some observations about what we might say. So the first thing that you would observe about this diagram is Calabi-Yao mirror symmetry. So let me go back. You look at the fact that everything that appears for one value of H11 minus H21, there's a value on the other side of that axis. So positive and negative X here, these appear in pairs. So this is mirror symmetric across the vertical axis. This was first observed by physicists, including by Candelas and collaborators, and also independently work in the gauge linear sigma model community. And at first, mathematicians didn't buy that this was actually going to be a general feature of Calabi-Yaos, that for each value of Hodge numbers, H11, H21, there should exist another Calabi-Yao with those integers interchanged. Of course, it was proven to be the case, and again, extended into homological mirror symmetry, Netherfield's metal, good stuff happening there. So mirror symmetry, powerful feature of Calabi-Yaos. The other things you might want to know looking at this data set is there a finite range in topological type appearing for Calabi-Yao threefolds, at least for these types of manifolds that we've built so far? For these data sets, of course, there is. For more general Calabi-Yaos, it's still unknown for threefolds, whether there's a finite range of topology. In the manifolds that have been constructed to date, the smallest Hodge numbers appearing are 1 and 1, the largest 11 and 491. In 20 years of studying Calabi-Yaos, of trying to extract their properties, this data set has been getting denser and denser, but not bigger, which is to say that the boundaries of this plot have remained intact in 20 years. The shape of the plot has a lot of structure, and we're going to return to why that is later in the talk. So specifically, if you go back here, the fact that there are these interesting, parabolic structures here that sort of get mirrored as you go further down. There's a lot of structure as to which topologies are actually appearing for threefolds, and you could ask, why is that happening? And as has also been discussed in, for example, Chuck's talk yesterday, it is possible to actually connect different dots in this diagram through so-called geometric transitions. So these are simple operations where the manifold becomes singular, and you can repair those singularities through simple surgery, for example, replacing a singular point by a two-sphere. There is, for all the known data sets, for example, the initial 7,890 CC threefolds, all of them can be connected to each other using simple geometric operations of this type, which are known in string theory to actually be legitimate directions in field theory. So you can actually extend the field theory through these types of transitions. A conjecture, actually even weaker than a conjecture, a so-called fantasy by the mathematician Miles Reed, is that all Calabi-Yao threefolds should be connected by these types of geometric transitions. So those are some initial observations we might make about the data set as we understand it so far. So in the following slides, I'm going to be taking a little bit of a deeper dive to trying to illustrate why this data set, at least for threefolds, might be finite, and how to characterize some properties of its structure. Now remember, for all of us, if you're not a mathematician, right? You want to say, as a physicist, I am seeing these Calabi-Yao geometries appearing in my calculation. I would really like to be able to constrain that set and say, this is the range of things that I can get, so that I could constrain something about the field theory that is underlying my real problem in a meaningful way. So I want to be able to extract physics information from a knowledge of what's going on with Calabi-Yau's. But if I say I'm going to work towards trying to characterize or prove to be finite a set of Calabi-Yau's, you might ask, is that actually a question, is that a task for a physicist to be doing? Shouldn't mathematicians do that? And the answer is it's partially yes. But I don't have space to illustrate today, but there's actually a remarkable interplay, at least in string theory, between the consistency of field theories that arise in string compactifications and this underlying geometry. So examples, for example, the range of Hodge numbers of Calabi-Yau threefolds. This has been strongly linked, for example, in six-dimensional compactifications of F-theory. You can prove that through anomaly cancellation conditions that you would have anomaly inconsistent field theories if you had Hodge numbers larger than the ones that have already appeared in this Kreutzer-Skarka dataset. So this 11,491 is actually a firm bound in terms of anomaly consistent 6D string compactifications. Likewise, this was work done by Waddy Taylor. I should have put refs on this slide and didn't. Consistency of 2D sigma models. Oguri and collaborators have looked at consistency bounds on possible H11 for all threefolds. Just to give another example, chiral indices and heterotic theories are related to Donaldson-Thomas invariants of Calabi-Yau's. So there's a bunch of structure there that can be explored in terms of consistency of field theory and consistency of Calabi-Yau background geometry. So there actually is potentially more information at the intersection of the math and physics of this than there would be just mathematically or physically alone. Okay. So let me give some practical tools that some of these you have seen before. Part of this was alluded to in Albrecht's talk. Let's ask the question, how do we determine if two Calabi-Yau threefolds are the same? We could ask this about fourfolds and higher as well, but let me start with threefolds. There's a very useful theorem by Wall from the 1960s, which shows that there is a vector of data that you can compile about this Calabi-Yau, namely its Hodge numbers, which we've already discussed, the triple intersection numbers of divisors within the manifold. A divisor is simply an algebraic hypersurface within the Calabi-Yau itself. So here you have a basis where ABC runs over however many independent divisors you could write down, and the second Chern class of the manifold. If you compute, all of these are integer quantities, so you compute this set of integers, and if it is different for two Calabi-Yau's, then he showed that these are not diffeomorphic as manifolds. The converse of this is also interesting. So if you say I compile that list of integers, it is the same, then that what Wall's theorem shows is that these manifolds could be the same as real manifolds, but not necessarily diffeomorphic as complex. So for our purposes, when I say there's roughly 1 billion Calabi-Yau threefolds known, what do I mean by that? There's only 500 million hypersurfaces in the Kreutzer-Skarka dataset, but by analyzing intersection numbers and other things that appear, you can estimate that there's at least 500 million, probably much, much more, distinct manifolds existing in that set by Wall's theorem. Another thing that's going to be important for the rest of my talk is that Calabi-Yau's also can exhibit substructure. And again, you've heard about this from a variety of talks this week, specifically the existence of fibrations. So the fibration is a surjective mapping from your Calabi-Yau manifold X, say, to some other complex manifold B. And the existence of such a fibration is deformation invariant, i.e. topological, for Calabi-Yau n-folds where n is greater than or equal to 3. So if you can see something about the substructure of the manifold, that also can characterize which Calabi-Yau's are available to you. And as we'll see, this breakdown of the manifold into fibration can actually give you a big handle on integrals over the Calabi-Yau, properties of its topological structure. A lot of interesting features, even the shape of its metric can be affected by the existence of this substructure. Also, a very key result, if a manifold is fibered, the number of T2 fibered Calabi-Yau threefolds is finite. So there's one data set of Calabi-Yau's that is proven to be finite, and I'm going to come back to that in an important way in just a moment. Okay. So let me just say, again, most people probably know this, but let me, for those of you that don't work with this kind of geometry, let me try and define things. So what does it mean to be fibered? What do I mean by substructure? So the simple idea here is to try and morally stack one simple geometry over every point of another. So the formal definition is a fibration is a continuous mapping, pi from X to B, such that for almost all points in the base, BB prime, the preimage of the projection map, i.e. the fiber, is homotopic, i.e. smoothly deformable. This property is called the homotopy lifting property. The fiber we define to be the inverse image of a point in the base. The base is some complex manifold. So examples for non-mathematically inclined folks, R2, for example, is a fiber of R over R. So at each point in a real line, you have a copy of another real line over every point. Likewise, the cylinder is a fibration of an interval over S1. So you have a circle. Over each point in that circle, you fiber an interval. The Mobius strip is interesting because, unlike my first two examples, this is a non-trivial fibration. Trivial in the sense that if I had a direct product of R cross R or a direct product of S1 across this interval, these would form these simple manifolds. But the Mobius strip is a fibration, again, of an interval over S1, but it has a non-trivial topology to it. It has a non-trivial twist as you move around the circle. Interesting result, Calabi-Yau manifolds must have Calabi-Yau fibers of smaller dimension. So the only fibers that are going to appear, the only fibrations are ones which have Calabi-Yau substructure to them. So for example, Calabi-Yau threefolds can have T2 or K3 fibers over some bases. If it's K3 fibered, then by topology, you can show that the base must be a P1. Okay, you've seen in Chuck's talk, for example, yesterday, the importance of special forms of fibered manifolds. So in particular, I'm going to be talking a little bit about so-called elliptically fibered manifolds. Just to get the terminology straight, I will say elliptically fibered, genus 1 fibered, or T2 fibered. The difference here is that an elliptically fibered manifold has this marked point, and that means there exists a section, i.e. a mapping from the base back up to the total manifold. If the manifold admits the section in addition to its projection mapping, then we say it is elliptically fibered. If it doesn't, if it just has the projection, then it's either genus 1 or T2 fibered. But if we have an elliptic fibration, there's a nice normal form that you've already seen in Chuck's talk, which allows you to write a description of a P1, 2, 3, 6 elliptic fiber over every point in some complex base manifold B. Here, UI are coordinates that live in the anti-canonical powers of the anti-canonical bundle over that base. These fibers need not be the same absolutely everywhere. So for generic points in the base, they are smooth T2s, but over special points in the base, those T2s can degenerate. These degenerations, again, we've heard in various talks, can have significance both for the physics in string theory as well as for amplitudes and other interesting applications. The reason that I'm primarily going to try and talk about manifolds that admit fibrations for the remainder of this talk is that they provide an important window into considering finiteness. So as I already mentioned, in work in the 1990s, Grassi and Gross showed that there is a finite number of Calabi-Yau threefolds that can be written as a T2 fibered over some complex surface, B. Basically, the proof goes by showing that because you have a mystery Calabi-Yau manifold, you can break it into a fiber and a base, and you can characterize which base surfaces you can have and then how complicated the twist, just like the Mobius strip, how complicated can you twist this T2 over every point in the base. This gives you a very powerful decomposition. Instead of talking about some general complex threefold or real sixfold, you're able to break it into much simpler substructure. This type of proof has been recently generalized by De Cerbo and Svaldi for bases for Calabi-Yau fourfolds and fivefolds that are elliptically fibered. This is almost a complete proof of finiteness for all elliptic 4 and 5 folds. There's a technical detail missing, but for the most part, it is strongly believed that those are also finite and nearly proven. So another statement about these special normal forms, there's a theorem due to Nakayama that says that if you have a Calabi-Yau threefold, which is elliptically fibered, i.e. genus 1 fibered with section, then it is birational to this special normal form referred to as a Weierstrass model. Again, this is this simple description of a P1, 2, 3 elliptic fiber over each point in the base. Weierstrass models are a central tool in the study of Calabi-Yau fibrations. And again, the sort of the big in for extracting physics is because you can break your manifold into pieces, fiber and base over each point. You can characterize which base geometries can arise. You can characterize how the fibers can degenerate over what codimension in the base, how singular can they get, how, what types of degenerations and completions can you write down. And a lot of work has been used, these sort of simple models, these simple descriptions of elliptic fibrations to try and span a huge description of a huge range of different topological types of Calabi-Yaus and describe what's possible. Waddy Taylor and collaborators in particular have done a ton of work on Weierstrass models within the space of toric Calabi-Yau hypersurfaces. They showed that, for example, this mirror symmetry description that I mentioned in that is evident in the Kreutzer-Skarka dataset in elliptically fibered manifolds can be broken down into fiber-wise mirror symmetry. There's also some very nice work by Paul Ullman along similar lines. So there's a bunch of interesting structure you might want to explore using very simple descriptions of fibered Calabi-Yau geometries. But let me take a step back for a second and say again, I'm trying to give you an overview of Calabi-Yaus. I'm talking about Calabi-Yau threefolds because these are, come with many topological flavors. So why am I going to focus on these fibered guys? I want to ask the following question, and this is one that my collaborators and I have thought about recently in some detail, which is, suppose we are given a mystery Calabi-Yau n-fold, and we would like to know, okay, we know that the set of fibered guys is finite, but let's take some general one out of the data set of all Calabi-Yaus. Doesn't need to be finite. Sorry, it doesn't need to be fibered. Can I ask, is it fibered? Is it genus 1 or elliptically fibered? You could also ask K3 fibered. You could ask detailed questions about what types of fibers it has, whether there are sections to those fibrations. And do we have a toolkit for actually deciding within a general set of Calabi-Yaus, where do the fibered ones live? Fibered ones are much simpler to characterize. They can be proven to be finite. You can calculate with them very easily. So where do these fit in this broader data set? So the first thing is that if you take known data sets of Calabi-Yau threefolds, the CC threefolds that were initially built by Candelas, the Kreutzer-Skarka toric hypersurfaces, you can make two immediate observations. The first observation is that almost all, and I mean that very strongly, almost all known Calabi-Yau threefolds and fourfolds are fibered. They admit elliptic K3, Calabi-Yau threefold fibrations if they're fourfolds, and so on. And the second immediate observation is that generic manifolds do not just admit one description as a fibration, they admit many, order tens, hundreds, or thousands of different vibration descriptions for one manifold. So what can we make of this? So let me, with my remaining time, try and give you a bit of a flavor of what that looks like. So here I have plotted the Kreutzer-Skarka data set of Hodge numbers of Calabi-Yau threefolds again. And these blue dots, this I took from a paper from Waddy Taylor from 8 years ago. This is much denser now. These blue dots fill in almost all the known points in Kreutzer-Skarka with elliptically fibered manifolds that also have that topology. So you can show that the topological types are very readily spanned by elliptic fibrations. You can do a bit better in terms of looking at simple data sets like the complete intersections in, say, products of ordinary projective spaces. I'm sorry about that. My desk phone is ringing. So for Calabi-Yau threefolds, for example, 99.3% of all the manifolds in that data set are fibered. And if you look at the data set of Calabi-Yau fourfolds built in products of projective spaces, these were also classified by Gray, Haupt, and Lucas a few years ago. It's even stronger, 99.9% of all those manifolds admit fibrations. So how do you tell that a manifold is fibered or not? So the first pass is, if you look at a manifold, here's a CC configuration matrix. Here is the ambient space. These two columns are telling you about the degrees of two complete intersection hypersurface equations inside this ambient space. And what you can see is that by the degrees, if I were to pick a solution to this first equation in red and then substitute it into the second, what I would get would be a cubic equation in P2. If you remember our single projective space description of Calabi-Yaus, that is n+1 degree inside a Pn. This is a Calabi-Yau one-fold. So over every point in the solution of this surface, I will have a T2 in this manifold. So from the algebraic description of this manifold, it is very evident that I have a T2 fibration. This need not be the only type of T2 fibration it emits, but it's pretty obvious to see that this is T2 fibered. Likewise, here's a Calabi-Yau fourfold below. In different colors here, I've highlighted this blue describes the degrees of an elliptic curve inside the first three projective space factors. If I add in the red to the blues, that gives me a K3 fibration to this manifold. And if I add in the green, that adds a Calabi-Yau threefold fibration of this fourfold. So this fourfold is fibered by threefolds, twofolds, and onefolds in a nested fashion. So it has a threefold fiber, which in turn is K3 fibered, which in turn is elliptically fibered. Okay. Point of interest, when you see an obvious fibration of this type from the algebraic description of the manifold, typically there isn't just one, there can in fact be many. So when you write down a CC manifold of this type, remember that the order that is appearing for the ambient space projective space factors And the order that I write the defining equations in, those are totally arbitrary. So I'm free to rearrange rows and columns as I like. So here I can rearrange these two manifolds to actually show that this particular manifold is the same one, just rearranging equations, rows and columns. And I can show that this is fibered over two different bases. Here a red base, this has a T2 fiber over a 1, 1, 1 hypersurface and a product of 3 P1s. This guy is elliptically fibered over P1 times P1. Okay, so the number of fibrations per sort of algebraic type of manifold, called a configuration, can be plotted for different manifolds. You can see here that the number of fibrations, the sort of multiplicity of what's appearing, can be plotted for CC3 folds. You can say how many of them have 5 fibrations, 10 fibrations, and so on, 35 fibrations. This is the 4 folds up here. Some of the 4 folds had 350 obvious inequivalent fibrations from this type of description. Okay, I'm running short on time, so I'm just going to give you a flavor for what one can extend further. What my collaborators and I have worked on is trying to say for a general elliptically fibered manifold, what I want to characterize is not just whether I can spot a fibration from the algebraic description, but whether the manifold is really fibered. So fortunately, there is a powerful mathematical result, which was formulated for 3 folds by Wilson and Noguiso, and conjectured to hold more generally for Calabi-Yau n folds by Kolar, which allows you to characterize whether the Calabi-Yau admits a fibration or not, purely in terms of intersection numbers of the Calabi-Yau, so topological data about intersection of divisors, and some statements about the cone structure of those divisors. So specifically, if X is a Calabi-Yau n-fold, then it will be genus 1 fibered if and only if there exists a 1, 1 class D, so divisors are dual to 1, 1 forms inside Calabi-Yau n-folds, such that this thing has D dot C greater than 0 for every algebraic curve within the manifold. Its intersection to the dimension of X power is 0, and its dimension to the X minus 1 power is non-zero. So this not going to be clear to this audience why you would be interested in this, but the point is it's actually a strong way to be able to unpack just from topological properties whether a manifold is fibered or not. So my collaborators and I tried to do this for some data sets of Calabi-Yaus, and what we showed, so I'm going to skip this slide. Basically, we gave sort of an intuitive description of what this criteria is providing for you. And what we wanted to do was to say, can we actually take a data set of Calabi-Yaus and exhaustively say how many of them are fibered? And again, can we see if this fibration structure is sort of ubiquitous in data sets of Calabi-Yaus? So we began with the oldest data set of Calabi-Yaus, the 7,890 CC3 folds, and we classified all possible fibrations that could arise. There's some technical issues to how you actually accomplish this that were hard to overcome. Not going to talk about them today. But let me try and show you the results. So of that 7,890 CC3 folds, what we found is that there are about 400,000, sorry, missing an O there, 400,000 fibrations for that data set as a whole. For example, there were 377,000 genus 1 fibrations and 200,000 nested K3 and elliptic fibrations that appeared. I can't give you a full number for the number of fibrations that appear in that data set because they can get very big, in fact, infinite for one manifold. So the anti-canonical hypersurface in a product of 2 del Pezzo 7 surfaces, that guy gave rise to 15,000 different fibrations. And in fact, one manifold, the so-called Schoen threefold, gives you a parametrically infinite set of distinct elliptic fibrations. This is a self-Beer manifold with Hodge numbers 1919 that crops up all over the place in string theory. All right. Here is the punchline for physics of what you want to actually extract from this. What we see is that we are able to actually analyze which Calabi-Yaus have fibrations. And we find that for this data set, they are essentially all fibered. And there are hints that in fact, all Calabi-Yaus with T2 fibers can undergo simple geometric transitions to those that do not. So you can connect fibered and non-fibered manifold in very simple geometric transitions. This was proven for H11 equals 2 by Wilson. With Waddy-Taylor, we're trying to extend this further. The scans that we have done so far on both the toric and the CC3 folds lead us to actually conjecture that all Calabi-Yau 3 folds with H11 greater than 19 will be fibered. So again, as people interested in amplitudes, why is this of interest? Because this description might allow you to simply decompose the mystery Calabi-Yau geometry that is determining your amplitude in a very simple way. So there is a possibility that this description may hold for everything and give you a clean handle on what you want to describe. So I will conclude here. Hopefully this broad overview has shown you Calabi-Yaus appear in a wide range of string and field theories. Their properties and finiteness can be an interesting intersection of math and physics. Relatively new work has shown that almost, in fact, essentially all known Calabi-Yau manifolds are elliptically fibered generically with multiple fibrations. And we're developing a toolkit for being able to systematically decompose these things into fiber and base. This might provide a window into finiteness in the future and hopefully a new set of computational tools that might be relevant. So with that, thank you for your patience and thank you again for a great week.
Yes, let's unmute for a moment in order to thank Lara. Yeah, so we are rather short in time, but I see David already raised his hand for what I hope is going to be a short question, please.
Yes, it's a wonderful overview. I'm reminded Ernest Rutherford said there are two types of science, physics and stamp collecting, and mathematicians are very, very good at stamp collecting, you know, in deep mathematical structure. But what happens to us is that we hit Calabi-Yau three-folds at 4 loops, but then we can go on to higher loops. So we're kind of going on the opposite, on the other axis from what you're doing. So can you look at the 3 folds that we find and the 4 folds that we find and see what it is that physics selects that's mathematically distinctive from this?
So there certainly is a lot of structure that you can extrapolate to Calabi-Yau n-folds. I gave a flavor of 3 folds just to show you of some of the complexity of characterizing these things that arises. But yeah, depending on what you want to know, there's some things that are very easy to extract for Calabi-Yau n-folds in general, some things that are harder. Indeed, you know, for certain families, so for example, you know, the one that has appeared in simple classes is, you know, a single hypersurface and a single projective space that appeared in a number of talks. That's very easy to characterize for any n. You can sort of say every possible property of that guy you want. So for some families, you can do things in arbitrary generality. The question is, can you characterize how many different types might arise for some amplitude? I guess that would be the question. So, you know, if you're sure you're only in a subfamily, then you're good. You could maybe calculate everything you want. If you would like to run that backwards and say, imagine that every, you know, one of these topological types might appear for some amplitude, what could you say that might be harder to characterize for?
Thank you.
Okay, thank you very much. And thank you very much again for this really amazingly clear and beautiful talk. Before we actually switch to Francis Brown's talk, I would like to ask you to unshare your screen such that I can actually share mine. And I'd like to do that by showing an announcement. So we